In the name of God, my name is Masoud. I'm a physics teacher. We are in Ferhua's website at your service to explain physics curriculum, grade 10. So far, we talked about chapter 2 from your textbook. We explained a lot of information about physics. Right now, I want to explain new section, which is the solids and their properties. Let's talk about the composition of solids in general. Actually, this chapter focuses on solid, this information. And solids in general, mostly I can say, have a regular structure. They have 3D, 3D networks. They are regularly packed. Particles are very close to one another. They don't have any, dramatic motion. They just vibrate back and forth, or I can say they just vibrate up and down. That's why they have a vibration. Right now I want to explain, this subject. Let's dive in with the lesson. Firstly, I want to explain composition of solid. It says right now we have a definition for composition. Composition is the way in which atoms are arranged mostly to form a 3D pattern. Mostly, I say. Well, you cannot say always solids have regular structure. Sometimes they have particles are arranged randomly, like plastic and rubber. I want to read it for you. So the first, after the definition, we have a tip here. Tip says composition of a solid determines. So composition determines what? What does it determine? Composition or structure of solid determines two things. Firstly, the type of the solid, whether it's crystalline, such as diamond, sugar, salt, and or non-crystalline, or we can say amorphous, such as plastic, rubber, glass. So, in general, there are two types of solids based on their composition. Firstly, we have, crystalline. They are regularly packed, like this one, like this figure. So this figure is a, model of what? Model of crystalline solids, like diamond, like salt, like sugar, right? And this is a molecular structure for, for example, crystalline solids, molecular. So if you take a look at this structure, molecules are regularly packed. They form a 3D pattern. This is called, crystal lattice. We can name it as crystal lattice. If you take a look at it, the particles are very, arranged regularly. They are packed to one another. But about the amorphous solid like this one, like plastic and rubber, and the last, and I can say rubber, plastic, glass. They are all amorphous or non-crystalline. If you take a look at the atomic structure, these atoms are not regularly packed. They, arranged in a random pattern. So we don't have a, 3D pattern here, right? This is and an example of amorphous, like glass and plastic. So composition actually matters. Composition of solids matters. Composition determines the type of solid, whether it's crystalline or amorphous. Let me ask you a question. I want you to go over it. Think about an example of, for example, crystalline solid. Think about it. Crystalline, you know what crystalline is? I explained it for you. A solid that has a regular, crystal, or I can say they have a regular pattern, right? They have a 3D crystal lattice. Think about it. Like what? Like, I'm sure you know it. Like diamond, like salt, like sugar. One more example or one more question. Think about an example of, for example, non-crystalline solid or amorphous solid. Yeah, think about it. Go over it. I'm sure you know the answer. So the answer is plastic or rubber, right? They are all, non-crystalline. atomic structure is not regular. It's not 3D, right? Let me show you something. For example, what's this? This is rubber, right? This rubber is this rubber crystalline or non-crystalline? Is it amorphous or crystalline? So this one is non-crystalline or amorphous solid. One more thing, this one. So we have a steel, let's say a screwdriver. We have a metal, metal. This metal is very, let's say, I can say it's steel, It's still made of, it's made up of iron and what? Iron and carbon. So this steel is crystalline, is not amorphous, right? So this structure of this steel is like this. But a structure of rubber, for example, rubber is like this one, right? So this one is amorphous solid. This one is crystalline solid. So what thing determines the type of solid? Go over it, think about it, guess the answer. So what thing, composition or structure of solid determines the type of solid, right? Let me explain one more thing for you. So we have some questions here, right? There are a lot of questions. I prepared it for you. I want to, let's say, discuss it with you. Question number 1. How do particles move within the solids? Think about it. I'm sure you know the answer because I explained it in previous lectures. How do particles of solid, let's say, move, right? This is the answer actually. They vibrate around their equilibrium positions in a very regular array. They have a very regular array. Particles, they just vibrate, They just, let's say, vibrate. They don't have any, for example, let me bring this one here. I want to show you something. So it says vibrate, vibrate. It talks about vibration. So vibration is important, This is the key for understanding the motion of solids, vibration. They just, let's say, jiggling up and down, or I can say they just move up and down. So this is the answer. Number 2, solids have dash or space shape and space volume. We have two things. We have two options. Either you have to use definite or indefinite. So think about solid. For example, this, let's say this marker is solid, Does it have any, let's say, certain shape or not? Does it have any definite volume or not? Of course. So it has definite shape and definite volume. So the best answer for both, let's say, spaces is definite. So it has definite shape. Here I can say, I can write definite shape and definite volume. Definite, right? Because they are, you cannot alter their shape, Question number 3. On the atomic scale, solids are made up of a space array of atoms or molecules. We have options, Either you have to use regular or irregular. So it says on the atomic scale, solids are made up of what? Actually, they are made up of regular arrays of atoms or molecules, especially when you, actually, mostly, I can say, mostly solids have regular pattern or regular array, right? Question number 4, particles of solids is spaced around their equilibrium position in an array, right? So we have two options. Either you use move rapidly or vibrate. And they don't move for, let's say, rapidly. This is the property of gases, especially. It's not for solids. That's why the best answer is vibrate. Let me erase this one. I want to erase it, or, excuse me. Let me erase the answer. So what's the answer? What's the best answer? I can say vibration is the best answer. Particles of solids vibrate around their equilibrium position in an array. Question number 5. Compare the amplitude of atoms' vibration with the distances among the atoms. What do I mean by distances among the atoms? I mean equilibrium position. So, especially in a solid state, actually, right? I want you to think about it. Compare between two things. Compare two things. Compare vibration. Look here, vibration and what? Vibration and equilibrium distances. Let me draw, let's say, a model for you. I told you atoms within the solids are very close to one another. They are packed regularly beside one another. That's why there's a very, let's say, close distance. There's a very close distance between, for example, two neighboring atoms, right? Here, the distance actually is measured in nanometer, right? It's very, let's say, very little, right? But what do you say about the vibration? Vibration of atoms are what? I can say vibrations are very, let's say, less than. Vibrations are less than the equilibrium distances. So that's why solids have a definite shape and definite volume. So let me read the answer. Vibrations of atoms is less than equilibrium distances, right? That's why this little vibration, let's say, provides the constant shape for solids, yeah? It provides the certain shape and certain volume for solids in general, right? Let's move on to another question, question number 6. Let me bring it up for you. Let me erase the other parts. So we have question number 6. Amplitudes of particles vibration, right? This is the question. Amplitudes of particles vibration of solids are, right? We have a blank here. How do you, let's say, fill the blank? Think about it. It talks about what? It talks about the amount. Amplitude means amount, yeah? Amount of particles vibration, amount of vibration of solids are space, the distance among atoms, right? It's like the previous questions, but in another form. Choose the best answer. A, amplitude of vibration is the same as the, for example, equilibrium distances. Is it greater than equilibrium distances? Is vibration smaller than equilibrium distances, or much larger? I'm sure you know the answer, and this is the answer. Excuse me. Let me choose it for you. This answer is the best answer. So vibration is the smaller than equilibrium distance, or distance between the atoms, right? Question number 7. What does the arrangement of molecules in material, arrangement of molecules in material means composition, right? It means composition. What does the composition of molecules in a solid depend on? What does it depend on? What are the factors that affect the composition of solid? Let me read the answer for you. Number 1, shape of the molecules. So composition depends on what? Depends on the shape of molecule. Number 2, temperature of material, temperature, right? Number 3, stress. Actually, let me explain, for example, temperature for you. We have, for example, any material, for example. We have, for example, this rubber band, yeah? This rubber. I want you to heat it, for example. Whenever you heat it and the temperature rises, particles of solid change their positions. They change their positions. That's why composition changes as temperature changes, right? That's why temperature matters in determining the composition of solids, right? What do you say about stress, for example? Stress. Does stress, let's say, have to do with composition or not? Does it have any effect on composition? Of course, yeah, it has effect on composition. For example, I want to show you something. For example, we have, for example, about the stress, right? We have a spring, for example. We have a spring. We have this spring, especially whenever you, let's say, whenever you press it, yeah, whenever you press the spring from both direction, what happens to the, for example, to the particles of solid? Actually, the particles come closer to one another. Actually, maybe you say, teacher, in previous lectures, we told that the solids and even liquids are not compressible, but I can say in the case of, for example, huge stress, in the case of, for example, applying a huge force, this thing happens actually. Equilibrium distances, or I can say distances between the atoms change, right? In the case of, for example, extremely high pressure, extremely high stress, so composition of solid changes, right? So stress has, let's say, has to do with composition, right? Number 4 factor, magnitude of their interatomic force of attraction. Magnitude of the interatomic force of attraction. For example, think about two different kinds of solids. For example, think about amorphous solid like or non-crystalline, amorphous or non-crystalline like rubber. I told you. So this ball is made of rubber, right? This is amorphous solid, right? And think about, for example, composition of this screwdriver that is made of steel. Yeah, it's made of steel. That's why this one is crystalline solid. This one is non-crystalline solid. So actually, I have a question for you. I want you to think about the force, interatomic forces existed between the particles of rubber, right? And interatomic forces between the particles of steel. Which one has the greater interatomic forces, actually? Which one has a greater interatomic force? Actually, this one, yeah? This one, crystalline solids, have stronger interatomic forces. So the magnitude of force determines the composition, right? That's why you cannot change the shape of this, for example, a steel rod, yeah? You cannot change the shape of it easily, but this one with a little stress or with a little press, you can change the shape of this material. So interatomic force of attraction between the particles of steel is greater than the interatomic force between the particles of rubber, right? They are factors. These factors that determine the, let's say, composition of solid. We have one more example, one more question. Question number 8. List 2 factors by which the atomic composition of solid varies. Think about 2 factors. Actually, in previous questions, we mentioned 4 factors, right? I want you to just mention 2 factors, as you like. Mention 2 factors among these 4 factors. Maybe you choose shape of the molecule. Maybe you choose temperature, no problem, because question needs you to bring 2 examples, right? To mention 2, for example, 2 factors, right? Either you choose, for example, a stress or magnitude of vibration, magnitude of interatomic force, as you like, yeah? You can choose 2 factors from these factors. So here I answered it like this. Number 1, temperature. Number 2, pressure or stress. Pressure or stress, right? And by the way, the answer is optional, no problem. It's arbitrary. Whether you choose, let's say, this one or this one, it doesn't matter. You are free, right? Question number 9. List the properties that are affected by different compositions of solid. List the properties that are affected. So, composition of solid, guys, it's very important. Composition, let's say, determines the what? Even it determines the properties of solid, right? Composition determines the what? Composition determines the type of solid, whether it's crystalline or amorphous. Composition determines the properties, let's say, the properties of solid. Like what? Like, for example, mechanical properties, thermal properties, mechanical or electrical properties, right? Magnetic properties. Let me give you an example for each quickly. Mechanical properties, like what? Like, for example, density, like volume, like this. They are mechanical properties. Thermal properties like what? Like thermal expansion. Yeah, thermal expansion. Electrical properties like what? Like electrical forces, attractive force, or, for example, repulsive force between the charged particles, right? Or electrical conductivity, actually, another example of electrical property. And the fourth one, magnetic properties. Magnetic properties like what? Like, for example, attractive force between unlike charges, or repulsive force between like poles. Excuse me. This one, I have to say like poles, not like charges, because we have magnetic property. I'm sorry about that. About the magnetic property, I can say attractive force among the what? Among the unlike poles, unlike poles, or repulsive force between like poles, right? They are magnetic properties. But in our textbook, especially, we focus on what? We focus only on mechanical properties. We don't, let's say, focus on thermal or electrical or magnetic property. We neglect these factors. We neglect these properties. We concentrate especially on mechanical properties, right? Let me bring it up for you. Right now, we have, let's say, diagram. I prepared the diagram for you. The diagram mentions what? Mentions the mechanical properties that are included in your textbook, right? Let me read the, let's say, properties for you. The first one, density, yeah, density. Number 2, rigidity. Number 3, elasticity. Number 4, tension. Number 5, stress. Number 6, strain. Number 7, Young's modulus. Yeah, we have 7 mechanical properties of solids, right? So we focus on these properties one by one. We define them one by one. We give some example of each. Actually, we have some notes actually for we have some notes for each property actually. The first one, density, right? Let me explain density for you. The first one, density. What's density in general? Density is the mass per unit volume of a substance. Mass per unit volume. Mathematically, I can say rho is equal to m over v. From now, we denote the density with rho. Yeah, rho, or you can say d capital, no problem. You can take the first word from the excuse me. You can take the first letter from the word density. You can take d, no problem. But this is in physics is very common. Rho is very common. Rho is not English word actually. It's a Greek word. Rho is equal to m over v. So I want you to look here. I have a question for you, and I'm sure you know the answer. I want you to drive the unit of density, especially, right? Drive the unit of density. And by the way, density is not fundamental quantity in physics. It's a drive quantity, because it's defined by 2 other, let's say, quantities. So mass is measured in kilogram, right? Divided by. Volume is measured in cubic meter. I'm talking about the SI unit, yeah, SI unit. Maybe you say, teacher, is there another unit for density which is not included in SI? No problem. I can say, yeah, we have another unit like what? Like gram for mass actually, and cubic centimeter for what? Cubic centimeter for volume. Maybe in chemistry you have one we have, let's say, one or two more units, like what? Like gram per milliliter. You can say gram per milliliter, or let's say, or so on, yeah? But here in physics, we focus on what? We focus on kilogram per cubic meter and gram per cubic centimeter. But which one is valid in SI? Kilogram per cubic meter is valid in SI, right? So, density determined. This is a tip, yeah? I prepared the tip for you. After the definition, let's say, I wrote the, for example, mathematical rule. After that, I mentioned the unit. These information are important. I want you to, let's say, focus on these information and keep it in your mind, right? Density determines, this is a tip actually. Density determines how close the atoms are from one another. So, if the atoms are very close to one another, I can say the density is great for this material. It has a high density. Let me draw a figure for you, and I want you to guess the, for example, density for each. I want to draw an atomic composition of two material. For example, this is the atomic composition for a solid. Yeah, right? This is the first one. And we have another composition for the second one. For the second one, we have this structure. Yeah? We have this structure. I want you to tell me about the density for each. Which one has a greater density actually? Which one? It says, based on this, let's say, note, it says, density determines how close, look here, how close the atoms are from one another. So, the closer the atoms are from one another, the greater the density is. I said the closer the atoms are from one another, the greater the density is. So there's the inverse relationship between what? There's an inverse relationship between density and, let's say, particles distances, yeah, between distances among the particles and what? And the density. Look here. So, particles in the matter number 1, they are very close to one another. So, density is high here. We have high density. What do you say about this one? Number 2. Particles are relatively far from one another with respect to the first one, actually. With respect to the first one, particles are away from one another. That's what here we have, let's say, low density. Density is not a lot, right? So this is the note. Density determines how close the atoms are from one another. So can I say, I have a question. I want you to think about it. Can I say the larger the atoms are, the larger the, for example, equilibrium distances are, the larger the equilibrium distance is, or the lower the density is? We can say this, yeah? The higher the equilibrium distance is, the lower the density. So I told you there's an inverse relationship between density and particles, let's say distances, yeah? Distance among the particles. We have some questions here. Question number 1. The SI unit, look here, the SI unit of density is gram per cubic centimeter, B, gram per cubic meter, C, A plus B, D, kilogram per cubic centimeter. Which one is valid in SI? Actually, they are all, for example, gram per cubic centimeter is right, it's true. It's the unit for density, no problem. This one, kilogram per cubic meter, is unit for density, no problem. But which one is valid in SI especially, right? This one is valid in SI, kilogram per cubic meter. Question number 2, choose the correct statement from the following. It's about the density. I want you to go over it, right? Let me bring it up for a better, let's say, vision. Number 2, choose the correct statement from the following. Which statement is true? Number 1, A. The closer the atoms of matter are from each other, the greater the density is. So it says the closer the atoms are, the greater the density. Is it true or not? Of course, it's true, yeah? It's the our tip, yeah? Our note. B, the smaller equilibrium distances are, right? The greater the density is. Do these options coincide with one another? Of course, they are reconciled with one another. They are corresponded to one another. That's why if you said the closer, look here, the closer the atoms are, right? If you said the closer the atoms are, what does it mean? Means the smaller equilibrium distances are. So they are the same. There's no difference. The closer the distances is, what's the meaning of the closest the atoms are? Means they're smaller the equilibrium distances. They coincide with one another. That's why they are, till now, both options are right. What do you say about this? The third one, C, rho is reciprocal to R. R means equilibrium distance. So rho is reciprocal. It's inversely related to what? Related to R means equilibrium distance. And by the way, this one is true. So all of the options are true, right? All of the options are true. Thank you for watching this video. I'm gonna, let's say, finish this lecture. I'll explain the other properties of solids in a next video. And bye for now.